Okay, this is chapter 8, day 1. We're doing confidence intervals. This is pretty cool stuff. So you obviously need a calculator. You don't necessarily have to have a graphing one, but it's kind of nice. There's mine. You need it. You're obviously your notes, and you're gonna need to find the formula sheet either online or if you made a copy of it. And if you remember, the formula sheet at the beginning looks like this. And this is the exact formula sheet that you will see on the AP stats test. And you're going to go to table B. So it's right here. It's after the z-score table, table B. And it has T critical values, and it goes all the way down to right down at the bottom here where it says infinity. And it has these confidence interval numbers down here. Okay, so you're going to want to go, you're going to want to get that table. We're going to be working with this confidence interval page. Okay, so get that all ready. And let's go to this here. I got a couple sentence frames for you right off. First thing is to understand the meaning and interpretation of confidence intervals and confidence levels. Now, we're only doing confidence intervals in this chapter for two things, for means and proportions. Means is a whole number, like the average points scored by Kobe Bryant in 10 games was 22. It's a whole number. The average SAT score is a whole number. That's a mean. A proportion would be a shooting percentage by Kobe Bryant, 48%. Or what percentage of kids like calculus as their favorite class, about 55%. So means and proportions, which are averages and percentages, okay? The goal of, as you can see from the cursor here, is to estimate or capture the true proportion mu or pi. Mu is the true mean, pi is the true proportion. And that's the goal. You're trying to estimate it from a sample. In politics, it's really important to be able to kind of know what is the true percentage of people that have confidence in the president, because they always do a president approval ratings are something measured weekly in our country for about 100 years. And the typical president's approval rating is in the high 40%. Usually over half the country disapproves of him. Once in a while, they'll be popular if some big moment comes that will happen, but usually it runs in the high 40 percentages. We don't really know the actual percentage of Americans that approve of the president, but we can estimate it by a sample. That's kind of the idea. In an election, you actually eventually know the truth. You know the true percentage that voted for a certain candidate. You'll actually know eventually. And the polls will try to estimate it. But most things we don't ever actually know. We just try to estimate them. Okay. How do you estimate? You have an estimate. Your estimate is X bar if it's a mean. It's P hat if it's a proportion. Then you're going to go plus or minus a margin of error. This is new, okay? The margin of error is made up of something called the critical value and the standard error. The standard error you learned in chapter 7. For a mean, it's sigma over square root of n. Actually, it's going to be S now because we're using a sample. And then for a proportion, it's going to be P hat. 1 minus P hat. 1 minus P hat is called Q, if you remember that, Q hat over N. Okay, those two things we learned in the previous chapter. So that's going to be nothing new. The critical value is the new part. This is actually really, really simple and logical and common sense. I think you'll be able to figure this out pretty easily. Okay. All right, so let me clear that. These I have put 4 stars by them because you're going to have to memorize these. I want you to memorize these sentence frames because they do happen. The typical question you get for confidence intervals is they'll ask you to, you may want to write this down, they'll ask you to calculate and interpret a 95%, I'm going to put CI, confidence interval, and then they'll have the prompt. Calculate and interpret. The interpretation is going to be this sentence frame right here. We are 95% confident that the true mean lies between blank and blank because the process we used is effective 95% of the time. If you memorize that, it's going to help you when they ask you to calculate and interpret. So let me give you an example. If you're dealing with the mean, let's say that you went and watched LeBron James play basketball for 10 games and you wrote down how much he scored. And based on that, you think his scoring average is somewhere between 20.1 and 32.2. Let's say you calculated that. I'm going to teach you how to calculate soon. So when they ask you to interpret it, you're going to say, I am, or we are 95% confident that the true average, or the average of LeBron James's scoring average, let's say. Let me try that all over again. We are 95% confident that LeBron James's scoring average lies between 20.1 and 32.2 because the process we use is effective 95% of the time. Okay. A separate question could be if someone asks you, what's the meaning of 95% confidence? Okay, that is a separate question. So if they ask you, what's the meaning of 95% confident? That's not the same as asking you to interpret an interval. If you interpret an interval, you're going to use that first sentence frame. If they ask you the meaning of 95% confident, that's different. It comes from this concept. When you are estimating things, you're sampling. And every time you do a sample, you're going to get a different result. And the theory is 95% of the intervals will actually capture the truth. Okay. So if they ask you generically, what's the meaning of 95% confidence? That's this sentence frames. If the process is repeated many times in the same manner, approximately 95% of the confidence intervals would capture the true proportion or mean, depending on what you're talking about. So these are different. These are different questions. We're going to practice them quite a bit. Okay. All right. Some key concepts. These are predictions about a population. These aren't exact things. All right. Okay, fine. So let's slide down to the next one here. Compare and contrast z-scores versus t-scores. Okay. Z-scores are going to be used for proportions. T-scores are going to be used for means, is what we're going to do. Okay. You could do a z-score for means if the standard deviation is known. I make a note of that right here. Okay. If a standard deviation is known, but that is so rare. Don't worry about it. Just do this. If you're doing a proportion, do a z-score. If you're going to do a mean, do a t-score. I hope that makes sense to you. And the difference is, let me show you. The t distribution has more room in the tails because it's a sample. But as the t distribution increases in sample size, it starts becoming a z distribution. It's kind of like one of those limits in calculus. On the table B that we're going to be using, this is kind of cool. This is the concept, okay? When we're using a critical value for a z, we're going to use this bottom number for a z. So 95% confident is going to be the critical value 1.96. Now, as of this moment, you probably associate 95% confidence with the number 2 because you memorized the 68, 95, 99.7 rule, where 68% goes with a standard deviation of 1, 95 goes with 2, and 99.7 goes with 3. Those were estimates. It's not exactly that. We don't have 68% of this chart, but we got 70. We know that 68% is about 1 standard deviation away. So 70 is about 1.036. 95 is not exactly 2 standard deviations away. It's 1.96. And we don't have 99.7 on the chart, but we get 99.8. And that's about 3.09. You can see how that works. There's the empirical rule, the 68, 95, 99.7 rule. There it is on there, okay? Now, if you're using if you're doing a t distribution, the numbers are a little different. So let's say you had 20 samples. So n is 20 for a mean. What we're going to do is we're going to go n minus 1, 19, and then we're going to go on this row right here at 19. And if we want 95% confidence for 20 samples, that critical value is actually 2.093. What we do is, as you increase your sample size, this number, these critical values will decrease until they reach a limit of the z distribution, which is 1.96. If you missed all of that, today we're only doing z curves and we're only doing proportions. So we're going to only be using these bottom numbers right here. We're only going to be using these today. So if you're lost, just focus on those today. Okay. All right. So let me go back to this right here. Okay, we got that. Just recall up here that x bar and p hat are the center of the distribution, and the standard deviation is going to be. These are actually going to be a little different here. This is the one we had before. We're going to use s over the square root of n, and this will be p hat 1 minus p hat. And please write this down over n. Okay, and 1 minus p hat could be q hat. I'm going to write that right here. P hat and q hat. You see that right there. You could write that right there. Okay. All right. So slide down a little further. And again, I'm still talking about proportions and means. So here's the formula to find the formula to find the confidence interval for a mean and a proportion. First, the proportions. This first one, you're going to take p hat, and then you're going to go plus or minus z star, and I'm going to show you what that is in a minute. It's the bottom page on table B, times p hat times q hat. Remember, that's 1 minus p over n. So this is the standard deviation, and this is how many standard deviations. So if you want 95%, it will be approximately 2 for z star, because you know that 2 standard deviations away will give you about 95% of the curve and make you 95% confident. That's a tie into chapter 2. If you wanted to be 99.7% confident, this number will be about 3, because 3 standard deviations away from the estimate should cover 99.7% of the possibilities, according to the empirical rule. Okay, that's the idea. All right, now same thing here. If you have a mean, we have a different standard deviation. But again, x bar is going to be our estimate. Okay, t star is going to be the same thing as z star. So again, if you want to be 95% confident, this t star number will be about 2, because 2 standard deviations away from the estimate should cover 95% of the possibilities. Okay, if you wanted to be 68% confident, a weird number, this number will be about 1, because you can be one standard deviation away from your estimate, which is X bar, and you'll cover about 68% of the possibilities. By the way, in the real world, 95% confident is the gold standard. Everyone uses 95%. I hardly ever see 90 or 99 or 80. They're all mathematical possibilities, but 95% is the gold standard that you'll see everywhere. Doctors, media outlets, everyone uses that. Okay. All right. So, and I did all of this right here. So here's your menu. P hat is your estimate. In other words, you could write the word estimate. Okay. So what percentage of kids love calculus? And you poll 100 kids and 42% say they love it. That's your estimate, 42%. That's the center point. Then you're going to go plus or minus from there. If you're dealing with a mean, okay, you ask 30 kids at the school, what was your SAT score? You get an average. That estimate is that X bar is the estimate for the real average of the whole school. We're going to go plus or minus off of that to get a range so that we capture the truth. Okay. All right. This is no different than when your parents ask you, when are you going to be home? You say it's okay, 11 o'clock, you're going to be home. But really, you're not going to show up at 11. Really, it's 11 o'clock plus or minus 15 minutes. You could be home at 10:45. It could be 11:15. There's a range in there. So it's kind of fun if you tell your parents, when are you going to be home? I'm going to be home at 11 o'clock plus or minus 15 minutes, and I'm 95% confident. Because you may not make the window between 10:45 and 11:15 every time because of traffic or whatever. Okay, it's that simple of a concept. Okay. The other things here, Z star is that critical value. This is how many standard deviations you want from the estimate. It's the same thing as T star for a mean. Q is 1 minus P, S is standard deviation, N is sample size, N is sample size. Fine. Now, for the rest of this lesson, we're focused only on proportions. Now, when I wrote these answers out, I wrote them out in whole numbers, and I probably shouldn't have done that. So I'm going to do this a little differently. You'll have both ways then. So find the expected proportion and the standard deviation of the sample in each situation. All right, if something happens 18% of the time, that's 0.18. And how do you write the standard deviation? That will be 0.18, okay, times 0.82 over 59. And if you crunch those numbers, we did this in chapter 7, so you should be familiar with it. It'll come out 0.005, I'm sorry, 0.05002. Okay? So that's how that'll work. All right, 3B. Expected proportion is, let me slide this up just a little bit. So we have a little more room. Okay. 3B, this is 0.26. Standard deviation will be 0.26 times 0.74 over 3125. That is a very large sample. That's going to drive that standard deviation to below 1%. I try to memorize, and I think I told you this in chapter 7, but 1,000 samples, between 1,000 and 1,500, the standard deviation will be about 1%. So if you get 3,000 samples, it's going to be less than 1%. So that's the general rule in a proportion. 1,000 to 1,500 will drive the standard deviation to about 1%, okay, depending on what the percentage is, okay? All right, next one, okay, is this one. So this is 0.3494. How did I get that? I went 29 divided by 83, that's all. Now, what's a pain about this is I got a bunch of numbers here. I would just round it 2 spots. So it's going to be, I'm going to say 35%. So 0.35, 0.65 over 83. And that's going to come out about 0.05233. It's better to write it in proportions, about 0.05, which is about 5%. Okay. So samples under 100 will run 5-6%, which is pretty high, because if you're looking to be 99% confident, you have to triple that, because it's 3 standard deviations away. So you don't want your margin of error to be 3 times 6%. That's like 18%. It's huge. This is why you want the standard deviation really about 1%. So you want between 1,000 and 1,500 samples, because if the standard deviation is 1%, if you want to be 95% confident, you just double it. So then you have a pretty small margin of error. Okay. All right. Item 4. Okay. Let's go over some basics of this. Okay. So confidence level, sample size. There's really just a few things that affect the margin of error that you could do. There's only really 2 things you can do. You can adjust the confidence level, or you can adjust the number of samples. The goal, if you watch my hands in the video, the goal is to make the confidence interval small. That's the goal. Everybody wants to narrow the range of possibilities. They don't want to widen it. More confidence widens it. So one way to artificially make it smaller is to ask for less confidence. Okay. If I want to be 99.999% confident, I could say something like, if my mom asks me when I'm going to be home, I could say I'm going to be home between 4 o'clock this afternoon and next Friday. That would be 99% confident, but it doesn't really help, right? So most, and I have the arrows here to talk about this. Let me just get into this. So the confidence level, if you crank up the confidence level, like to go from 90 to 99% confident, the interval will rise. Okay. If you lower the confidence level, the interval will shrink. Okay. Now, sample size works this way. If you lower the sample size, the interval gets bigger. We don't want that. If you raise the sample size, the interval gets smaller. Okay, that's the one you really want. So 2 ways to shrink the interval. 2 ways. 1, get more samples. That will make the interval smaller. 2, lower your confidence. Okay, which most people don't want to do. Okay. All right. Now we're going to now get into some more calculations on this. Okay, so be cool. We're gonna focus on proportions. I'm gonna really break the skill down for you. Now the margin. Remember the formula. The formula for a proportion is going to be your estimate, p hat. Whatever your estimate is, that's called the point estimate. Plus or minus z star. Z star is simply how many standard deviations do you want to be on one side or the other of the estimate to cover the possibilities. And this is p hat 1 minus p hat over n. So this should be hat and hat. Okay. For means, it's going to be this over here. And go ahead and just write this down for now. Write this down, but we're not going to get to this today, but just write this down. Okay, that we're going to be using the T distribution table called table B, and we're going to go n minus 1, rounding down. We'll talk about later, but just get that on your paper for now. We're going to focus entirely on proportions because it's slightly easier. Okay. Okay. Now, so go ahead and have this particular sheet handy. And so real quick, again, Z's always use the bottom number, the infinity number. Okay, so it's really easy. If you go into T's for means, you have to go n minus 1. So let's say you want to be 95% confident for a mean. and you have 22 samples. 22 samples minus 1 is 21, and 95% confident gets me to that number is going to be 2.08. That's how that works. If you had 39 samples, n minus 1 is 38, but the chart doesn't have every possible number. So just estimate it at 30, round down, is going to be this number. That is not what we're doing today. I'm just showing you that for the means. For the proportions, it's really easy. We're just going to do this part of the table the rest of the video. This is for proportions. It uses the infinity one because it's a z. Okay, so we're using that. All right, so we're going to go back and forth here quite a bit. First one, find the critical value for 90%. All right, we know 95% is about 2, right? 2 standard deviations away. So 90% is going to be a little bit less than 2. Okay, so we're going to go right to here, and 90% is going to be this number, 1.645. So if you want to be 90% confident, you need to estimate 1.645 standard deviations on each side of your estimate. Okay, so that's pretty simple. All right, the next one, and I know I'm repeating myself, 99% confident. Well, we know 99.7% confident is going to be 3, because 99.7% of the data is within 3 standard deviations. Okay, so 99% is going to be a little bit less than 3. You see the answer of 2.576, no problem. Let's grab it right here. 99% confident, right there, 2.576. Okay, so again, if you want to be 99% confident, you need to get 2.576 standard deviations on either side of your estimate. Your estimate is p hat, okay, plus or minus. Z star is how many standard deviations, and your standard deviation is this calculation. We did it in chapter 7 quite a bit. Okay, so once again, if you want to be 99% confident, you got to get 2.576 standard deviations. That's that one on either side of your estimate to cover the possibilities of error that you could have made in your sampling technique. Okay. All right. So next one is 80% confident. That's a very strange number. Nobody really uses 80%, but it's mathematically possible. Well, 68% is 1 standard deviation away, so it's more than that. So 80%, pretty easy to find. Here is 80%, 1.282 standard deviations on either side of your estimate. We'll cover the possibilities. Okay. All right. Now, we're going to go backwards. This is pretty simple. We're going to go backwards. If you had a critical value of 2.326, what confidence level would that be? No problem. If you had a confidence level of 2.326, I know if I had a critical value of 2, that would be about 95%. So this is going to be a little more than 95%. Because the critical value is a little bit more than 2. 2.326. 2.326 is right here. Yep, there it is. 98% confident. All right, because that could happen. You could have to go backwards. All right. Next one is 1.96. This one I am begging you to memorize. Please memorize 1.96. Okay, that one is so common. It's the 95% one, but let's check it out, okay? I told you it was 2 as an estimate a long time ago, but so 95% is 1.96, okay? And then the last one, or the next one, is 1.645. This is another good one to memorize. It's really common too. 1.645 is 90%. Let's go over here and check it out. 1.645 is indeed, oops, that's the wrong spot. 1.645 is 90%. Okay, very cool. All right. Now, we're going to go ahead and do some calculations, okay? We're going to calculate just the margin of error. That's the part after the plus or minus. So let me do this again. It's p hat plus or minus z star times p hat 1 minus p hat, which is called q, over n. This part is the margin of error. The margin of error is made up of two parts, the critical value, z star, and the standard error, which is p1 minus p over n square root. Okay? So find the confidence interval. Find the margin of errors. I'm going step by step. So find the margin of error. No problem. Find the margin of error. Okay? Let's see here. All right, the margin of error. So I'm going to go ahead and write this real big on here, but so I'm doing G right now. So find the margin of error. I am going to go 95% is 1.96. Trust me on the chart, okay? And that's going to be 0.64 times 0.36 over 28, okay? And it comes out, I have it written right here. If you calculate this, stop the video and calculate yourself. It comes out 0.1779. It's about an 18% standard error. That's really huge. Okay, it's so big because n is 28. You have such a small sample size. That's a massive margin of error. Okay, I wrote it in whole numbers. Margin of error is 17 or 18%, but if you write it this way, it's probably better. 0.1779. Just rounded two spots, about 18%. Okay. So H, okay, H, we got 80% confident. Okay, 80% confident is 1.28. Okay, times what is 38 out of 103? Let me bring my calculator up to get that. Let's see here. 38 divided by 103. It's about 37%. I'm going to round about 37%. Okay, about 37%. So I'm going to go, all right, so I'm going to multiply that times 0.37, 0.63 over 103. Okay, again, stop the video and crunch the number. It will come out about 0.06091. It'll be a little different than that because I rounded. Okay. And again, I wrote the answer initially in whole percentages. Most of the time you write it in proportions. Okay. All right. Next one. 47 out of 65 at 98% confident. What was 98% confident? I don't memorize that one. 98 is 2.326. I have it in the sheet right there. 2.326. All right. No problem. So I'm doing this problem right here, 2.326 times 47 out of 65. I don't know what that is, but I'm going to find out. Okay. 47 divided by 65. 0.72, good enough. 0.72. Okay, and again, I'm rounding 0.72, 28 over 65. And that comes out about 13%. It'll come out 0.1291, so about 13%. Okay, that's all done by hand. All right, and now we're going to go majorly backwards here. In the next part, I'm on 4J. I'm going to go backwards here. And this could happen. I've seen these problems in multiple choice form, where they give you the confidence level I mean, they want you to find the confidence level, and they've given you the margin of error. Okay, so let's try this. So what we got here is the margin of error is 0.057 okay, making it a proportion. That equals, okay, we don't know the confidence level. We don't know Z star, so I'm going to put Z star in here. This is just algebra. And we're going to do 0.83, 0.17 over 123. So stop the video and set that up for yourself. So now I'm going to have to do some calculations here and find out what Z star is. Okay, so the margin of error was this, about 5.5%, 0.05572, equals Z star, how many standard deviations times the margin of error there. So let me bring the calculator up and get it into a spot where you can see it. Okay, perfect. Okay, so I'm going to go, you can see the on there. So I'm going to go 0.83 times 0.17, enter. I'm going to go real slow, divided by 123, enter. And I got a second square root second answer. So I'm square rooting the whole thing. So what I did is I did this part right here, 0.83, 0.17 over 123. Now to solve for Z star, I'm going to go 0.05572 divided by second answer. I don't want to do any rounding, so second answer that I had there. And I get 1.645 for Z star. So I solve for Z star, okay? So Z star equals 1.645. Oh, I got a message on here, that's cool. 1.645, okay? Now, the question is, what is the value of Z star when it's 1.645? All right, no problem. Let me reduce this. 1.645. Let me change colors and leave this all on here. Let's see here. 1.6, I got it right here. 1.645 is 90% confident. So that's the answer, 90% confident. You can see the answers in red right there, okay? And I will circle that answer again right there. It's a lot of work to get that answer, okay? All right, let's do K and L. Set those up, okay? Make it a little bigger here, a little more room. That's good. Okay, so put this over a little bit. Okay, so here's K, okay? I'm working on K right here. 27 out of 88, I really don't know what that is, but let me check it out. So clear all this. 27 divided by 88 is 0.31. 0.31 is good enough, probably 0.31. All right, fine. All right, so I'm going to have the margin of error is 0.12664. Okay, it's in. I had it in whole numbers. I made it into a proportion. Equals Z star times P, 0.31, I rounded, times 0.69 over 88, P1 minus P over N. Now I'm going to solve for this right here first, okay? And you're going to see this on the calculator when I bring it up, all right? Okay, so we got, let's try it all on one keister, see if I can get here. Yeah, I don't like to do that. Let me clear that. I'm going to go 0.31 times 0.69 divided by 88. And I'm going to get the square root of that, second square root, second answer. Did I get the whole thing? All right, I'm going to leave that there. And I'm going to go 0.12664 divided by second answer, then that. And then now I've solved for this. So I have some rounding, but this looks, I got 2.568. Let's find the closest one to this, 2.568 on this. 2.568 is probably closest to this one right here, 2.576. So it's probably 99%. Because I rounded that percentage, that threw me off a little bit, but you get the idea. Okay, so the answer is 99%, which we'll go back to see the answer there. It'll be right there for you. Perfect. The next one, let me move my face here, is 53 out of 74. Again, I'm going to have the rounding issue, but let's figure out what 53 divided by 74 is. Okay, 53 divided by 74. 0.72. Again, I'm going to have some rounding here. 0.72, fine. Okay, 0.72. So I'm going to go 0.10272 equals, because that's the margin of error, Z star, which I don't know, times 0.72, 0.28 over 74. All right. Bring out the calculator once again. Again, you may want to stop the video at this point and try yourself. That's always good to do. 0.72 times 0.28 divided by 74. All right, and then second square root, second answer. All right, fine. And now I'm going to take the 0.10272 divided by the new answer, second answer. And I'm going to get about 1.96, about 1.96. I memorized that one as 95%. Let's check it out. Okay. Yeah, 1.96. Yeah, it's 95%. Okay, so that was the Z star on that one, called the critical value, 95%. And you'll see that when we go back to the answer key here, 95%. Perfect. All right. Last section, very conceptual. We've talked quite a bit about how to reduce the margin of error. Okay. Again, if you look at my hands, the goal is always to reduce the margin of error, because you want the interval smaller because you want to be more confident. You want to know, pinpoint things in statistics better. All right. If we went from number one, if we went from 1,000 samples down to 100, that's not going to give us, it's going to give us less of an idea of what's going on, which means it will increase the interval to cover the possibilities. If you go from 50 to 100 samples in number two, that's going to decrease the interval because you have more information. More information decreases the possibilities. Now, this degrees of freedom, DF is degrees of freedom. Degrees of freedom is for means, not proportions, for means. And all you do, if you had 1,000 degrees of freedom, that means you had 1,001 samples. So all this is saying is we're going from 1,001 samples to 101 samples. That's all it's saying. And I'm trying to teach you degrees of freedom, okay? And that will, of course, will increase the interval because you have less information, okay? Here's the reverse. Let's say we had 1,001 samples, and we're going to increase that to 2,001, okay? Obviously, again, degrees of freedom is n-1, and there's a reason for that, but it's just kind of beyond the scope of this particular course, so just trust me on this, okay? That will, of course, decrease the interval because you're increasing the sample size, which makes the interval smaller, okay? Now, if your Z star is 95% and you're going at 1.96, if you make Z star bigger, you're going to increase the interval. That makes total sense, right? It's a bigger number being multiplied, Okay. So if you want 1.96 standard deviations away from the estimate, and you increase that to 2.676 standard deviations away from the estimate, clearly you're going to increase the interval. Okay. Here's T star. T star is for a mean. T star is for a mean. If you go from 2 standard deviations away to 1.5 for your estimate, you're obviously going to decrease the interval. Okay. If you go from 95% confidence, 95% confident is 1.96 for a proportion. And you go down to 90% confident, which is 1.645. That's a smaller number, so you're going to decrease the interval, but you're less confident. Now, if you go from 80% confident, I think 80% is 1.282, I think, and you increase it to 90, which is 1.645, you're clearly going to increase the interval. Remember, there's 2 ways to make the interval smaller. The preferred way, get more samples. Option 2, reduce your confidence. That will shrink the interval. Okay? There's 2 ways to increase the interval. Less samples increase the interval, and more confidence increases the interval. Okay? All right. That is chapter 8, day 1. Thanks a lot.